All right, 6.3, scalar multiplication. So in a nutshell, what we're doing here is finding multiples of a scalar. Um, sorry, multiples of a vector. So for example, if I had a vector A right here, okay, and I wanted multiples of it, vector A, vector A, vector A, and I have four of them, that'll give me 4 times vector A. Simple as that. Okay, so scalar multiplication. If k is bigger than 0, then we have k, k number of v vectors in the same direction. If k is less than 0, then we have k number of v vectors just in the opposite direction. If k equals to 0, then we just have the 0 vector. That's it. Okay. Collinear. Any two vectors are the scalar multiple of each other. So it has to be the same or opposite direction. Collinear just means they line up. They're on the same line. Okay. So vector A, B, and C, all three of these are collinear. If I drew a vector D, not collinear because it's not facing the same or opposite direction. Yeah. So scalar multiplication, if k is 0, well then you get 0. You get the 0 vector. Okay. So these two are just showing examples. If k is bigger than 0, so then we have vector OB, okay? And then we look at vector BD, for example. So this is just showing a distributive property, vector A plus B. If I have multiples of it, then distributive property essentially applies. Okay? Now here you're just representing different vectors. Okay, so for example, express each of the following vectors in terms of only A and B. Okay, so vector A is the red, vector B is the blue. So what's AB then? So AB, maybe I should use, let's use green. So we're looking for vector A, B. Okay, we're looking for this vector. Oh, that's terrible. Let's try that again. Vector A to vector B. How do I represent that using only vectors A and B? Well, AB I can tell is going to be from A to X, and then from X to B. Well, since I see these little ticks, meaning they're equal length, I have two of those vectors, right? They're both length of vector A, so then AB can be rewritten as 2 times vector A. We have two of those red vectors to find vector AB. How about DA? DA, so we're looking from vector D to vector A. Well, you can already see we're going to have two vector B's except in the opposite direction, so negative B vector plus negative B vector to give me negative 2B vector. And then vector xy, where's xy? Oh, xy is over here. So we're looking for vector xy. So how do we get there? Well, you're going to go from x to a, and then a to y, right, to give xy. Well, x to a would be the same thing as the a vector, just negative, right, plus b to give me xy. Okay? Linear combination of vectors. So if v and u are non-zero, non-collinear vectors, meaning they're not zero and they're not on the same line, then any vector O to P in the plane containing u and v can be expressed as a linear combination of u and v. What does that even mean? That just means that any vector ever can be represented by, in the 2D world, can be represented by two vectors v and u. V, or u and v. Okay? So how does that make sense? Well, any vector, for example, if I just do that, right? That's just a random vector I drew, okay? And I have the vector, let's this u, and I call this vector v. How could I represent this vector with just those two? Well, I can see that. Again, I just randomly made these vectors up. Looks like I need 3 of those, right? So 3 u's plus, so v, so again, I'm going to move it over here. So 1, let's say I need 2 of those vector v's, plus 2 v's, will give me my green vector. Let's call it W. And that's it. Okay, that's what this is saying. This proof is optional. You can read it, but it's just saying any vectors can be represented by multiples of the vectors u and v. Okay. Any questions? Again, shoot me an email.